The focus of this video lecture is going to be on Nash equilibrium. It's the topic of Chapter 9 in your textbook. You may be familiar with the name Nash. John Nash won a Nobel Prize for his work pioneering this particular equilibrium concept. He also has made significant contributions in mathematics, and the movie A Beautiful Mind starring Russell Crowe was portraying John Nash in the movie. So Nash equilibrium, the chapter 9, we're going to be focused in this chapter on pure strategy Nash equilibria, so equilibria in which every player in the game is adopting a pure strategy. It means it's just one strategy for sure and not a probability distribution on her strategy space. In the next video lecture, we're going to discuss mixed strategy Nash equilibria, which is the topic of chapter 11. We're going to be skipping chapter 10 in this course. All right, so rationalizability, are the last subject that we spent a lot of time discussing, permits miscoordinated beliefs, right? So rationalizability, oops. Rationalize. Boy, I can't spell. Miscoordinated beliefs. That was our second strategic tension of game theory. So we use iterated dominance, we find the entire rationalizable set. Sometimes that set is a single strategy profile, sometimes it's not, and when it's not, it's possible that players believe other players all play within the rationalizable self. They themselves choose the best response to whatever their particular belief is, but they could be wrong in their belief, right? So the strategy they adopt makes sense in the sense that, like, given their belief, and the belief is reasonable for under the common knowledge of rationality, given that belief this is what they should do, they turn out to make a bad guess, right? And that's a very common sort of notion that people would not always be perfect fortune tellers, right? They'd often be wrong in a one-shot game of what they think the other player is going to do. Okay, so rationalizability isn't enough to get rid of what we call strategic uncertainty. So you're not sure what the strategy adopted of everyone else is, right? So, for example, suppose X and Y are rationalizable for you and A and B are rationalizable for me. All right, so our strategy space, whatever it was, has been reduced to a rationalizable set of just two strategies for each of us. Okay? What if I think you'll play X, in which case the best response for me is A. That would be a perfectly reasonable thing for happen, right? So if I think you're going to play X and the best response for me to X is A, that makes perfect sense, as long as X is rationalizable. Okay? So I have rationalizable beliefs. I think you're going to play X, and so I play A. Okay? Your best response. but you actually play Y. And so it was wrong. All right, I made a guess, a reasonable guess, an educated guess, but it was a wrong guess. Okay, so I could be in a game like this. 2 by 2. After iterated dominance, so this is R, the rationalizable set. We have the following game that survives iterated dominance. Okay, like suppose 3, 2, 0, 0, 0, 0, 2, 3. All right? And I think that I'm player 1, and I think that you're going to play X. And if I think you're going to play X, A is the best response for me. So I play A. But it turns out you played Y, and the reason you played Y is that you thought I was going to play B. So we both ended up being wrong, right? So we both ended up making reasonable guesses, but we're wrong, right? So this is possible within the rationalizable set, right? So profiles A and X, AX, and BY. Oops, those aren't the ones I want to talk about. Excuse me. Profiles AY and BX reflect miscoordinated beliefs. Okay? Whereas in AX and BY, we are both correct in our beliefs and played a best response. This is the key of Nash equilibrium. Okay? So in AY and BX, we can interpret those profiles as players being incorrect in their beliefs of what is going to happen. Profiles AX and BY, both players were correct in their beliefs of what would happen given a best response to that belief. So if players are best responding, those reflect correct beliefs, and that's going to be the key feature of Nash equilibrium. We're both going to make a guess about what the other player is doing within the profile. The guess turns out to be correct for both of us, and we're best responding to that guess. And everyone is best responding to the play of everyone else in the profile because they believed that's how everyone was going to play. Okay, more formally, the definition of Nash equilibrium. Strategy profile S, which lives in the space of all strategy profiles. Notice that here I'm only adopting pure strategy profiles, S. I'm not looking at sigma because I don't want to worry about probability distribution profiles yet. We'll worry about that in the next chapter. Okay? So a pure strategy S is a Nash equilibrium if and only if player I's strategy within that strategy profile is an element of that player's best response set given the belief that S minus I is being played. So given the belief that everyone else is choosing S minus I and being correct in that belief. Right? So player I choosing SI is a best response to the strategy profile that everyone else has adopted. Okay? That has to be true for every player I. Or in other words, the utility to player I of playing S when everyone else is playing S minus I has to be greater than or equal to the utility of player I of playing S prime when everyone else is playing minus I. For all possible S prime, Si prime, that live within player 1's strategy space, and for each player I. Alright, that's our definition of Nash equilibrium. So we first think about a profile, a specific profile. We ask, is that profile a Nash equilibrium? That profile is a Nash equilibrium if and only if every player's SI, so every player's strategy within that profile, is a best response to the choice of everyone else, so to the strategy of everyone else in the profile. So fixing what everyone else has done, I'm doing the best I can within that profile, and that's true for every player, which means that the utility I get from playing SI, given what everyone else has done, is greater than or equal to the utility I would get from doing anything else that was possible for me, given what was done. Okay, and again, we're restricting ourselves to pure strategies here. Okay, and I don't have to. Even though we're restricting players to choosing pure strategies, I know that if the utility of SI is at least as big as the utility of SI prime, then it's going to be, so it's bigger than all the utility from all possible SI primes. Then any mixed strategy that between those SI primes is also the first one's going to be bigger, right? So if the utility of SI, given what everyone else has done, if that utility is 5, and that's greater than or equal to the utility of every other pure strategy that I could have played, well then of course a mixed strategy of all those other pure strategies would also be less. So I don't actually have to worry about comparing it to all possible sigma I. I just have to compare it to all the pure strategies. That makes our life a whole lot easier because we don't have to worry about comparing SI to an infinity of possibilities. So that's nice. All right, so this is a formal definition of Nash equilibrium. So I'd next like to look at several famous 2x2 games, sort of canonical 2x2 games that economists look at, and think about the Nash equilibrium in those games. Okay, so the 2x2x2, I mean there's 2 players and each player has 2 strategies available. You've already seen this one. I believe you've seen several of them at this point. But, so this is the prisoner's dilemma. Now in the prisoner's dilemma, of course, prisoner's dilemma. In the prisoner's dilemma, we already know that the unique rationalizable outcome is both players defecting, both players playing D. So of course that is also going to be the Nash equilibrium of this game. All right. So we already know that C is dominated for both players, right? And so this will be the Nash equilibrium because the Nash equilibrium has to be rationalizable. Like, it's not possible for a profile to be in equilibrium if it's not rationalizable. We only have to worry about the rationalizable set. But to see that it's an equilibrium by the definition that we've given, imagine player 1 plays D. Well, what should player 2 do? Of course, it's better to play D than to play C. A payoff of 1 is better than a payoff of 0. So given that player 1 plays D, player 2's best response is D. And of course, given that player 2 plays D, player 1's best response is D. So they both believe the other player plays D and they make the best response to D. All right? And of course, this game even has a stronger prediction. It's that you don't even need Nash equilibrium. You just need rationalizability, right? All you need, all you need is rationality. We don't even have iterated dominance here. We just have a dominated strategy C right off the bat. We just need rational players. We know they're going to play D, but it does also correspond to our Nash equilibrium. Okay. More interestingly, here's another 2x2 game. Player 1 and 2 both have the strategy A and B. And the payoffs here are 1 and 1, 1 and 1 in this corner, 0, 0, 0, 0, This is the coordination game. So, if I think you're going to play A, I will also play A, and if I think you're going to play B, I will play B. So both players would like to mimic what the other one does, but it's a simultaneous move game. Okay, so they don't know, they have to make a guess, right? So under rationalizability, both A and B, of course, are rationalizable. Each one is the right thing to do depending on what your beliefs are, all right? But so because the entire game is rationalizable, we could see people playing profile AB and profile BA, but those are not equilibrium profiles, right? Someone made a mistake, right? They both thought they were both incorrect in their beliefs in that outcome, right? Whereas these profiles AA and BB are Nash equilibrium. Each player is doing the best he can given his belief, and his belief is correct about the other player. All right? Souping up the coordination game a little bit more is the Pareto coordination game. So we still have strategies A and B. This time we're going to ramp up the payoffs of that upper left corner to 2 and 2, but otherwise it's the same. So we'll call it the Pareto coordination game. Okay? That game, what makes it even just a little bit more interesting, so we still have two Nash equilibria. The entire game is still rationalizable. This is a Nash equilibrium, and this is a Nash equilibrium. But one of those equilibria is efficient, and one of those equilibria are not. So the AA equilibrium is the unique efficient outcome of the game, and BB is not efficient. Okay? So this highlights the fact that just because an outcome is a Nash equilibrium says nothing to us about its efficiency. We could have efficient equilibria and we can have inefficient equilibria. So the two concepts are very much disconnected. Okay? So in this particular game, if I'm player 1 and I believe that player 2 will play B, then I absolutely should play B. And if I'm player 2 and I believe player 1 plays B, then I will also play B. So BB is a Nash equilibrium. Both players are doing the best they can, given their beliefs, and their beliefs are correct. Okay? But the equilibrium AA would dominate BB from an efficiency standpoint. And the concept of efficiency that we're using in this class is Pareto efficiency, which is why we call this one the Pareto coordination game. Behaviorally, we often expect in lab, or we observe in laboratory experiment environments, that players typically coordinate on AA, because the fact that it's the efficient equilibrium gets people to focus their attention more and believe more that the other player will play A, which makes they themselves more likely to play A, and it's kind of like a self-fulfilling prophecy. Okay, but I mean that's beyond the scope of this class. But behaviorally, in the coordination game, you really can get behavior all over the map. Each one of those is equally likely, all four of them. Whereas in this Pareto coordination game, we do tend to see people adopt profiles more like AA more frequently than anything else. Okay? And then another game that again is kind of like a coordination game. It's historically called Battle of the Sexes. The title itself is pretty sexist, but the profession still hasn't changed the title. So the strategies are opera, movie, opera, movie. We have partner 1, player 1. Think of this as a romantic partnership. Player 1 prefers to go to the opera. Player 2 prefers to go to the movies. Historically, gender roles, the idea was that the woman would prefer to go to the opera, the man would prefer to go to the movie. Who knows if that would even be true on average anymore, but that was the original idea of the game. These games were all created in the 1950s. So the idea is that player 1 prefers the opera to the movie, player 2 prefers the movie to the opera, but both players prefer doing an activity together rather than doing their own thing. So notice that player 1, even though she prefers the opera to the movie, that she still gets zero utility if she goes to the opera if her partner ends up going to the movie. So they miscoordinated in that case. And same for player 2, right? So in the opera equilibrium, player 1 it gets higher utility. In the movie equilibrium, player 2 gets the higher utility. This can make beliefs hard to coordinate upon, right? So it's like on player 1, I would prefer to go to the upper left equilibrium, but I know that player 2 would prefer the lower right equilibrium, so how do we coordinate our beliefs in that kind of environment? So everything's rationalizable, but belief coordination is a challenge there. It's kind of like, is there a stronger person we all think that person's going to go to the one that they like, and the other person believes that, so that makes them more likely to coordinate on that one. So yeah, that one again, just like with the Pareto coordination game, it kind of goes beyond the scope of this class and gets more into behavior, like economics type issues. All right, but we have 2 equilibrium profiles there. There are 3 other 2-player, 2 strategy games 2x2 games that I'd like to talk about. This is the Hawk-Dove game, also called chicken. Okay, you can either be a hawk, tough guy, or you can be a dove, softy. And if both players decide to be hawks, it's not good. They both get 0. If they're both doves, they both get more utility. But if player 1 decides to be a hawk and player 2 decides to be a dove, player 1 gets a really big payoff and player 2 gets a relatively small payoff, and it's reversed over here. Okay? Alright, so Equilibria, well, if player 1 is going to be a hawk and player 2 believes it, then player 2 should definitely play dove. And if player 2 becomes a dove, then player 1 was correct to play hawk in the first place. So this is an equilibrium, as is this one. Okay? So these equilibria, kind of like Battle of the Sexes, are asymmetric. Right? So one equilibrium is good for player 1, the other equilibrium is better for player 2. But in addition to that feature, it also has another efficient strategy profile. So the equilibrium profiles are efficient, but so is the dove-dove profile. It's not an equilibrium profile, but it's rationalizable, and it also reflects kind of cooperation and mutual kind of reinforcing choices. So it's not equilibrium choices, but it's choices that kind of do well overall for the group, right? So it kind of throws that feature, kind of like the prisoner's dilemma. So you can think of this as maybe combining Battle of the Sexes with a bit of a prisoner's dilemma flavor, and that there's this other profile out there that makes them both relatively happy, but they're not able to play it in equilibrium. Okay? Another game called Pigs. So you have this pig and one pig. I forget exactly what these stand for now that I look at it. One pig is dominant and the other one is passive. I think that's what P and D stand for. So the payoffs are 4, 2, 2, 3, 6, 1, and 0, 0. Okay, so if you're a dominant pig and the other pig is passive, so if player 1 is dominant, player 2 is passive, player 1 gets really, really high payoffs of 6, the passive pig only gets 1. If they both try to be dominant, they both get nothing, etc. Okay, so but it's asymmetric unlike Hawk-Dove. So it's kind of like the Hawk-Dove with some asymmetry built in. And so I think the storyline goes that there's a button that the pigs have to push in order to open the food chute, but the button isn't close to the food chute. So a passive pig goes over and pushes the button, and as soon as he pushes the button, the dominant pig who's standing by the gate jumps into the food and gets most of the food. So there's not much left by the time the passive pig gets there. But if they're both dominant, they both stand by the food gate, but it never gets opened because they're both waiting for someone else to push it. If they're both passive, they both walk over and push it and come back and get a more evenly split meal. I guess player 1 is a little bit stronger overall to begin with. So how does this game end up being played? Let's see. Does someone have a dom? So let me think. Yeah, so if player 1 plays P, then player 2 will play D, and if player 2 plays D, player 1 will play P. So this is a Nash equilibrium, this profile. Again, player 1 plays P, player 2 will play D. The best response is D, and if player 2 plays D, player 1 will indeed play P. And then down here, so if player 1 plays D, player 2 will play P, and if player 2 plays P, player 1 plays P. So we have two Nash equilibria in this game. Okay, I now realize that I wrote the wrong game for pigs. I should have changed the payoff. So this I analyzed this game correctly, but this game wasn't the pigs game. So the pigs game is very close to that game, except it's the following. P, D, P, D. This is still 4, 2. This is 2, 3. This is still 0, 0. This was 6 and minus 1. So there's a big penalty for player 2 if she plays passive and player 1 plays dominant. Okay, so otherwise the game is the same. But the whole time I was looking at the game, I was like, something doesn't feel right. I don't think there's supposed to be two equilibria. With these particular payoffs, now we have that player 2 has the dominant strategy to play dominant, because like its outcomes under the passive pig are so bad that this pig has to, even though she's not the stronger pig, she has to play dominant just to end up she'll definitely do better by playing dominant. So P is dominated for player 2. And since P is dominated for player 2, player 1 knows player 2 will play D, and given that player 2 plays D, player 1 has to play P. So kind of the stronger pig with the kind of the greater utility associated with being dominant actually ends up being the one who has to be passive. So it's kind of a role reversal in that sense. So anyway, this one. In this case, this game has a single equilibrium. That equilibrium is also the unique rationalizable outcome of the game. So these aren't, both players don't have dominated strategies, but through iterated dominance, we get two unique rationalizable set of PD, and that is also the Nash equilibrium in this game. Sorry about that, writing the right game wrong in the first place. And finally, one more game, and this game is a bridge to Chapter 9. This game is called Matching Pennies. So you put a penny behind your back, you place it down on the table at the same time as the other player puts it down on the table. Player 1 wins the penny, so he gets to take back his own penny and gets the other penny from player 2. So that works for player 1 when both come up heads or when both come up tails. Right, so player 1 makes money when both coins come up on the same side. Otherwise, player 2 makes money. Player 2 gets the pennies when the heads and tail, when the two faces don't match of the players. All right. Now this game, if player 1 chooses H, player 2 would prefer to play T. But if player 2 plays T, player 1 prefers to play T to match it. But if player 1 plays T, player 2 prefers to play H. But if player 2 plays H, player 1 prefers H, and they keep going around and around and around the circle. So in this game, there are no pure strategy Nash equilibrium. Okay, so to think about equilibria in this game, we're going to have to use the techniques that we learned about in Chapter 11, which is mixed strategy equilibria. So we're going to have to both players adopting a mixed strategy. There is going to be a mixed strategy equilibrium in that particular case, but there are no pure strategy equilibria in this game. Mm-hmm. There is another little definition I want to give at this point. So a profile is kind of like an auxiliary definition for Nash equilibrium. A profile S is a strict Nash equilibrium if the utility to player I of playing SI, the equilibrium strategy, is strictly greater than this player's utility adopting any other strategy. For all Si prime in S and for all I. So for every player I. Notice this is the same definition we had for Nash equilibrium, except instead of greater than or equal to, this is a greater than sign. So a strict Nash equilibrium is that every player has a unique best response in that equilibrium profile. So given what everyone else is doing, every player's choice is unique, right? So in some sense, strict Nash equilibria can be thought of as stronger than non-strict equilibria, because if an equilibrium is not strict, that means one player, given what everyone else has done, has multiple options of best response, and one of those options for sure is the equilibrium option. But if that player moved to an alternative, that destabilizes the equilibrium, because then everyone else's choice may not any longer be a best response because that player switched. So a strict Nash equilibrium is kind of like a more robust and more like a stronger sense. The intuition of why the players would stick there if they believe that they're going to get there, it's stronger for a strict one than a non-strict one. All right, so that's just a little extra definition thrown in there. So in general, we actually have an algorithm for finding Nash equilibria, for finding pure strategy equilibria. It turns out to be quite easy. What we're going to do is underline best responses. And the double underlines, I'll explain what that means shortly, are the Nash equilibrium. All right? So I'm going to explain what I mean there through an example. So here's a game. Player 2 has 3 strategies available. Player 1 has 4 strategies available, pure strategies. Player 1 can play J, K, L, M, and player 2 can play X, Y, and Z. Let me populate this game. 5, 6, 3, 7, 0, 4, 8, 3, 3, 1, 5, 2, 7, 5, 4, 4, 5, 6, 3, 4, 7, 5, and 3, 3. Okay? Now, what's the double underline exercise? Well, suppose that player 1 chooses row J. So suppose player 2 believes player 1 chooses row J. What's player 2's best response? Well, of course, it's to play Y. So let's underline that 7. It corresponds to the payoff of the best response. Okay? In row K, if player 1 is going to play row K, the best response of player 2 is to play X. So let's underline that payoff for the best response. If player 1 plays L, player 2's best response is to play Z. And if player 1 plays M, player 2's best response is to play Y. Okay? Now let's look at the perspective of player 1, thinking about what player 2 does. If player 2 plays X, the best response for player 1 is to play K. If player 2 plays Y, the best response of player 1 is to play M. And if player 2 plays Z, player 1 has 2 best responses. He can either play K or can play L. Okay? Our double underlines are KX, LZ, and MY. The fact that they're double underlines mean each player is best responding to the other in that particular profile. So looking at KX, if player 1 plays K, we already know player 2 does the best she can to play X, and if player 2 plays X, player 1 does the best she can by playing K. So KX is a Nash equilibrium profile. It fits the definition of an equilibrium profile. So are the other 3 that have been circled. So there's 3 Nash equilibria in this game. I'll again repeat, there are 3 pure strategy Nash equilibria. Okay? We'll talk about mixed strategies in our next lecture. Okay, so some things about Nash equilibria I want you to keep in mind. All strategies in a Nash equilibrium profile are rationalizable. Right? If a profile, if it's at least in a game, at least in a game without, let's see, it's certainly true for a 2-player game, and it's also true for a more than 2-player game, provided you allow for correlated beliefs. But if a strategy is rationalizable, it means it's a best response to something, right? So if a strategy is not a best response to something, well, then it can't be a part of an equilibrium, because equilibria are a best response to something, right? So a profile has to be rationalizable in order to be an equilibrium, because an equilibrium requires that the strategy be a best response, and if a strategy is a best response, then it's definitely true that it's a best response to something, then it must be rationalizable. All right. So all strategies in a Nash equilibrium all Nash equilibria profiles are rationalizable. That's probably a better way to put that. All right. And so you can always imply iterated dominance before you look for Nash equilibria. Right. So you can execute iterated dominance if you like. Some games have more than one. And you see one right beside us, right? There's 3 equilibria in this game. That means that in those games, that the belief coordination requirement is even stronger, right? So if Kx is an equilibrium, but requires that not only do we play an equilibrium, but we both believe that we're going to play that one, right? So we have to think about, how do players coordinate on equilibria when there's multiple equilibria? Like what's to make, when I look at this game, I'm not allowed to think we're going to play the Kx equilibrium when in fact you're playing L as player 1 because you think I'm going to play Z. We're not allowed to be miscoordinated in these multiple equilibria. Okay, so that means that there's a really strong, there must be something that helps us coordinate our beliefs towards the equilibria. The way that's usually explained is that games like this are often repeated. So they're repeated a number of times, and over repetitions of the game, we kind of hone in on one of those profiles. And so after having played a profile for a number of rounds, and we expect that thing to come, then we if that's the profile that we believe is going to be adopted, it's an equilibrium profile if I have no reason to pull out of what we've coordinated on doing, right? So if you repeat a game, and the last 100 rounds, I'm player 1, you're player 2, we played KX, and so I'm pretty sure that you're going to play X again. Well, if I'm pretty sure you're going to play X again, well then I should definitely play K, and vice versa. And so repetition can help us coordinate on a Nash equilibria. There are other explanations as well, but again, like these games we've been playing as if they're one shot and they're not repeated, and if they're repeated, it's a bigger game, so we have to model the repetition process. It gets complicated. So we're kind of abstracting, we're definitely abstracting from the process by which people actually know how to coordinate beliefs on that particular equilibrium, okay? So that's just something to keep in mind. It can be quite a strong assumption, right? So some games do have more than one Nash equilibria, and some games have no pure strategy Nash equilibria. And for example, matching pennies was such a game where there was no pure strategy Nash equilibrium. Okay, two more things I'd like to do with this lecture is to revisit the partnership game, the strategic complements game, and then introduce the oligopoly game, one that you saw in Introductory Micro, but we're going to look at it in its full glory because now we have tools to think of that game in more detail. So reconsider the partnership game. This is the game where player one, the profit of player one, again we're using pi to stand for profit, the profit of player one was equal to 2x plus y plus cxy, where x and y are the efforts of player 1 and 2 respectively, restricted between 0 and 4, c is a parameter between 0 and 1/4. Player 1 is giving the effort x and it's costly, so player 1 plays a cost of that effort, it's quadratic cost. Player 2 splits half the firm's profit, which is the same as player 1, is 2 times x plus y plus cxy, and plays a cost for herself. And as we did a while back, we solved it in Chapter 7 using calculus. I'm not going to go through those derivations again. The best response of player 1 to a belief y bar, we're calling that best response x star, and x star is equal to 1 plus c times y bar. So whatever player 1 thinks that player 2 is going to do, he multiplies the belief of C's behavior by C, adds 1 to it, that's the best that player 1 can do, and the best response of player 2 to her belief about what player 1 does, we called that y star, and that is equal to 1 plus C times x bar. And again, this comes from Chapter 7. Okay, we use calculus to solve that. In a Nash equilibrium, beliefs are correct so best response is x star equals 1 plus c times y star, because player 1 knows that player 2 chooses the best response to player 1's action. It's an equilibrium. So player 1 knows that player 2 chooses the best response. It's not just any old y bar, it's the best response y star. And player 2 is going to be correct about player 1, and they're both going to believe that the other is correct in their beliefs, etc., etc. So x star equals 1 plus c times y star, and y star equals 1 plus c times x star, which means we can substitute one into the other. So therefore, that little arrow with two equal sign and an arrow means therefore. X star is equal to 1 plus c times 1 plus c x star, because y star is equal to 1 plus c x star, so we're just substituting one into the other. So that equals 1 plus c squared x star. I can subtract 1 minus c squared from both sides. I can subtract c squared times x star from both sides. So that gives me 1 minus c squared times x star is equal to 1 plus c. So x star is equal to 1 plus c over 1 minus c squared, which is equal to 1 plus c over 1 minus c times 1 plus c. The 1 plus c and the 1 plus c cancels out, so the whole thing is equal to 1 over 1 minus c. Okay? So x star equals y star, because it's a symmetric game, so if we solve for y star, we plug x star in for y star, we're going to get the exact same thing, which equals 1 over 1 minus c. This is our Nash equilibrium. Okay? And by Nash equilibrium, I mean that the profile is player 1 chooses 1 over 1 minus c, player 2 chooses 1 over 1 minus c. So that would be S star, the Nash equilibrium profile. Okay? So for this particular game, if both players are correct in their beliefs and they're both best responding, it implies that the Nash equilibrium profile is 1 over 1 minus c. So as long as we know the parameter c, we know exactly what both players should do in the equilibrium. Of course, in this game, it turned out that that was the unique rationalizable outcome as well. We solved for that. That was hard to solve for. We had to apply limits. In equilibrium, it was a lot easier to solve, just the algebra. Plug one equation into the other. Okay, and again, that should have been anticipated because all Nash equilibria have to be rationalizable. Okay. All right. I don't want you guys to worry about congruous sets. So the topic of congruous sets comes up in Chapter 9. You're not responsible for. So I'll say not responsible. So ignore that in Chapter 9. The last thing I want to talk about in this chapter, the last game, is Cornell Oligopoly. Right, this is a topic we talked about at length in introductory microeconomics, wherever you took that, whoever you took it from. So in this game, there are n identical firms. Constant marginal cost, which is equal to C for every firm. So that means that every unit that a firm produces costs C units to produce. I'm sorry, a price of C to produce, a cost of C to produce. No fixed cost, so we're just going to make life easier on ourselves. No fixed cost. Simultaneous choice, so every firm makes their decision independently and simultaneously. So firms are picking quantity simultaneously. Then market demand determines price. Okay, so the production idea here is that it takes some time from the point that you decide how much you're going to produce to the time that you actually produce it. So a bunch of firms have to decide how much they're going to produce today, and then they can't get it to market till later. And then once all that quantity actually makes it to the market, the sum of the quantity of all the individual firms, the market demand curve will then determine what the price is. We'll go through the actual mechanics of how that happens, but that's the basic idea of the model. So everyone has a constant marginal cost, no fixed cost, and they produce the identical products, and they each one choose a quantity, and then later on, the sum of the quantities determines the price. So they have to make a guess of what the price is, or the sum of quantities is of everyone else. And given that guess, they make a choice of quantity, but then the market will actually determine what the price is. Okay? The demand in the market is given by a standard demand curve. So demand is given by price equal B minus M times Q. Okay? So B is the y-intercept of the demand curve, and M minus M is the slope of the demand curve. All right? So price is a function of quantity. This is a linear demand curve, so it's exactly what you would have seen in introductory microeconomics with a y-intercept and a slope. Okay, so simple model. That's the demand, and we're going to let qi, little qi, equal the quantity produced by firm I. Okay, and then note that capital Q, the total quantity in the market, is just equal to the sum from I equals 1 to n of all the individual firms in the market, right? So every individual firm produces QI. If you sum up all those individual QIs, it gets you the total quantity in the market. We can rewrite that total quantity in the market as the quantity of firm I plus Q minus I, where Q minus I is the sum of quantities excluding firm I. That's going to be important for us. So we want to note that the total quantity in the market, which is the sum of all the individual quantities, can be broken into two parts, firm I's part and for everyone else in the sum of everyone else's part. The reason we want to do that is firm I gets to choose what QI is, but doesn't get to choose what Q minus I is. Firm I has to make a guess of what Q minus I is, and then from that guess, choose the best response of quantity to send to the market. Okay? So the profit of firm I, we'll still let pi be profit, is equal to, let's see, it's equal to, price times quantity minus marginal cost times quantity. All right? And so price times quantity is total revenue, and cost times quantity is total cost. So it's just total revenue minus total cost, right? So you sell QI units, you get a price P per unit, that's your total revenue, price times quantity, and then each unit costs you C to make. Okay? So that's your profit in the market. Right? Simple enough. Okay? So that profit, I can substitute P, I have an expression for that, because I know that P equals B minus M times Q. So I have B minus M times Q times my own quantity minus C times my own quantity. Okay? That's that's profit in the market. Okay, but I know that that big Q is equal to the sum of some little q's, right? So I can say that the profit of firm I is equal to B minus M. Instead of big Q, what I'm going to put in here is QI plus big Q minus I. All right, so that's just, that part is just equal to big Q. And it's that whole thing times QI minus C times QI. Okay, that's a very big step. Okay, it's a very important step. So again, I know that B minus M times big Q is price in the market, and now I'm substituting in for big Q the fact that big Q is equal to firm I's output plus everyone else's output. All right, and now I can rewrite that expression as B times QI minus M times QI squared minus M times big Q minus I times QI minus C QI. Okay? Now, firm I forms belief Q minus I bar. Again, we always express beliefs with a bar on top of the variable. So firm I has to form a belief about what everyone else in the market is going to do. So everyone else has a little QI. Firm I forms a belief about the sum of everyone else's quantity, because if she knows what the sum of everyone else's quantity is, plus her own quantity, she knows what the price is, which means she knows what the profit is, and then she wants to maximize that profit. Okay? So expected profit under that belief is pi I, which is equal to let's see, B minus C minus M times the total quantity believed to be in the market times, so I basically combined all my terms that are multiplied by QI, and then minus M times QI squared. Okay? So this is expected profit in the market, and that's going to equal the sum of all this stuff, B minus M minus B minus C minus M times my belief of what everyone else does, times QI minus M times QI squared. Okay? Note, B minus C minus M Q minus I bar is just a constant. right? So that whole expression inside of the parentheses is a constant. B is a B, M, and C are parameters of the model. Okay, we keep them as variables because we're the economists. We want to think about how the solution to the problem changes if we change cost, or if we change the slope of the demand curve, we change the y-intercept. So they're parameters for us, but for the individual player, they're numbers. She knows exactly what those numbers are, okay? And Q minus I bar, also a number. She takes a guess of what the total quantity in the market is, okay? Just like in another game that we looked at, it's the only reason we're allowed to take we can abstract from mixed strategies that we know it's a pure strategy guess, is that this is going to be a quadratic maximization problem, and so that is going to allow us that even if there is a mixed strategy, the mean belief is going to get us an equivalent payoff to the pure strategy that adopt the mean of the belief. Sorry, a distribution of beliefs. If we think of the mean of that distribution, the mean of that distribution will get us exactly the same expected payoff as as choosing a pure strategy of that belief itself. And so we're not losing anything by only thinking about pure strategies here. Okay? If that sounds a little confusing, don't worry about it. Just let's suppose we're only dealing in pure strategies, and that's fine for the purpose of for the purposes of what we're talking about here. Okay? And beliefs Q minus I bar. And again, that's just a constant. Like, do I think everyone else is doing 50? Then that's 50. If I think everyone else, the sum of their quantity is 80, then that number is 80. Whatever that belief is, it's just a number. So that whole thing is a bunch of numbers. So the only variable in my profit is QI, which means I can take calculus to it. Okay? Again, if you have multivariable calculus, you can think of Q minus I as a variable, but we're going to take the partial derivative of profit with respect to my own choice, fixing that at some level. But if you haven't had multivariable calculus, just treat it as a constant. We're not losing anything by doing that. Okay? So the derivative of profit with respect to firm I's quantity is equal to, well, it's a constant times Q, so we just get rid of Q. B minus C minus M Q minus I bar minus 2 times M times QI. Okay? The second derivative equals minus 2. So this profit function is concave in the choice variable, in QI. Okay? So set that slope that we just started for, the first derivative is the slope of the profit function. Set slope of the profit function equal to 0. That value of QI is optimal. Okay? Whatever value of QI makes the slope equal to 0, that's going to be the optimal choice of QI. So we have B minus C minus M times Q minus I bar minus 2M. The optimal value of Q star, the optimal value of QI, which we'll call Q star, is where that slope equals 0. All right? Which means that QI star is equal to B minus C minus M times the quantity that everyone else produces, or my belief about what they do, divided by 2M. Okay? That's our best response function. Okay? But now let's think about equilibrium. Okay? So look, my best response is a function of the three of the parameters. Now remember, I have 4 parameters. I'm going to write that a little bit better. So I see the best response is a function of B, C, and M. Those are 3 of my parameters. I also had a parameter N, but qi star is not directly a function of n, because all I need to know is the sum of everybody else's quantity, my belief of what that is, right? So n's kind of there implicitly, because the more firms there are, the bigger I think that total quantity of everyone else is going to be, all things else being equal. But all I need to do is form a belief about what that total quantity is, and then I don't have to worry about n directly. Okay, so n doesn't appear in this equation, but q bar minus I does. All right. Okay, so in equilibrium, of course, my beliefs have to be correct, right? So qi star equals q minus I. Sorry, q minus I bar equals q minus I star. Well, what's q minus I star? Well, it's a symmetric game, so all of those firms have to have the same best response function that I do, right? We all have the exact same profit function, the same marginal cost, everything's the same. So whatever I do is the same for everybody else. So how many everybody else's are there? There's n minus 1 of them. And they're all going to do the same as me. So n minus 1 times qi star. And this is since q star, the total equilibrium quantity, is just going to be n times my own quantity, right? Again, there's n of us. My own individual best response is qi star. The n of us are all going to do the same thing. I know they're going to have the same best response function as me. So whatever I do, the total quantity of the market is going to be n times whatever I do. So the total quantity of the market in equilibrium is going to be q star, which is equal to n times whatever I do. And since q minus I star is everybody but me, there's going to be one less firm doing that. So the q minus I star is going to be equal to n minus 1 times little qi star. All right? So I'm going to substitute that in to my best response function, b minus c minus m times, now I'm going to make that substitution, because I know that in equilibrium, that's going to equal n minus 1 times qi star divided by 2m. Okay? And so that means that I want to multiply both sides by 2m and get the qi star on the right hand side. I want that to the left hand side. So I'm going to have 2m qi star plus m times n minus 1 qi star equals b minus c. Okay? And now I can combine my qi star terms. So I'm going to have 2m plus m times n minus m, the whole thing times qi star is equal to b minus c, which means that m plus m times n times qi star equals b minus c. And then m plus m times n is equal to m times 1 plus n times qi star equals b minus c. So the equilibrium quantity for each individual firm is b minus c over m times 1 plus n. And now here you notice that when we looked at the best response function, it was a function of three of the parameters and the belief of q minus I. Now in equilibrium, we're going to be correct in our belief, so we know what everyone else is going to do. They're going to do the same thing that we do, and so we're basically able to substitute out for that belief. We substitute back in an n, right? Not directly. We can't replace q minus I bar with n. But we're substituting our belief of q minus I, and we're able to replace that with a function of the number of firms. All right? Because again, we can collapse q minus I star to a function of my own individual quantity and the number of firms in the market. Okay? So this is our equilibrium quantity. All right? And since that's the individual equilibrium quantity of the firms, and all the firms do the same thing, big Q star, the equilibrium quantity market, is just n times that thing, right? So it's just n times bigger than Qi star. And that's going to equal B minus C over M times N over N plus 1. All right? That's a useful way of writing it for the following reason. So imagine the limit of the equilibrium quantity imagine equilibrium quantity in the limit as n goes to infinity, right? Perfect competition. So as n goes to infinity, we approach perfect competition. Right? As the number of firms gets infinitely large, like every individual firm becomes arbitrarily small relative to the market, and they become a price taker, right? So we're approaching perfect competition, then Q star approaches, well, we had B minus C over M, I believe. I'm going to check that real quick. Yeah, times N over N plus 1. But N over N plus 1 in the limit as n goes to infinity approaches 1. It actually approaches it quite quickly, right? So Q star, big Q star, is simply equal to B minus C over M, right? So that's the equilibrium quantity in perfect competition. Okay, what about price? Well, I have a formula for price. Price is equal to B minus M times Q, but if that Q is the equilibrium quantity, then of course price is the equilibrium price, okay? So price is equal to B minus M times B minus C over M, which equals B minus B plus C, which equals C, right? So P star equals C, or price equals marginal cost, which, if you're paying attention in introductory micro, is one of the fundamental concepts of perfect competition. We always have price equal to marginal cost pricing in equilibrium. So here we derive it, okay? And we also see that the individual quantities of the firm, so we look at the individual quantity here, okay? That individual quantity, as n gets really, really big, that denominator gets really, really big, which means overall Qi star gets really, really small relative to the market, right? So Qi star approaches 0 as n approaches infinity, which is the idea that every firm is arbitrarily small relative to the entire size of the market, but the market we can express as n times Qi star, and that n over n plus 1 disappears, right? That converges to 1, and so we're left with what the quantity and prices would be under perfect competition, okay? For monopoly, the best response of individual firms, we had Qi star equals B minus C minus M times Q bar of Q minus I bar. Well, under monopoly, Q minus I bar equals 0. There are no other firms, so the quantity you expect from all the other firms is 0. So Qi star equals, just rewrite from the other page, equals B minus C minus M Q minus I bar over 2M, so that that Q minus I bar disappears. Okay, and so quantity in and since only one firm, the quantity of that firm equals the total quantity in the market, all right? And so quantity under monopoly is half Q star in perfect competition. Okay? So quantity under monopoly is B minus C over 2M, and quantity in perfect competition is B minus C over M. So it's half as much under monopoly as perfect competition. So the market is twice as big under perfect competition as it is under monopoly under linear demand curve, right? So all bets are off if our demand curve is not linear. So I'm assuming when I make that statement that we have linear demand as we've derived here. But now you see perfect competition, you see monopoly, and you also have what is the equilibrium quantity in when we're not at either one of those extreme cases where n is equal to 1 or n is equal to infinity. So our equilibrium quantity overall, the total quantity in the market, is B minus C over M times n over m plus 1. So whatever the value of n is, you can tell, then we know exactly what the quantity is. That quantity in the market is increasing as the number of firms increases. So it's as small as possible under monopoly. It's as big as possible under perfect competition. The more firms there are, the closer we get to perfect competition in quantity, and the closer the price drops to marginal cost. Okay? So that's a lot of what we learned in Introductory Micro. We spent a lot of time in Introductory Micro talking about oligopoly and what the monopoly does, and what perfect competition does, and then looked at the Nash equilibrium of Cornell Oligopoly. Here we're putting all of that stuff together into one comprehensive model, and we can think about what the model implies when n is equal to 1, when n is equal to infinity or approaches infinity, and when n is an intermediate case. All right. So this is a good kind of discussion of a recap of what you learned before, but it's a richer recap because we are able to put a lot of mathematical structure on results that back in Introductory Micro we just said take our word for it, right? Yeah, as you add the number of firms, the total quantity in the market increases and the price drops. Now you actually see it. You see the derivations of why that's true in the case of linear demand, which is what we assumed in Introductory Micro as well. All right? And that concludes our lecture on Nash equilibrium. So to recap, the things that you learned is that in equilibrium, everyone's belief is correct, and no one has an incentive to unilaterally deviate from the equilibrium strategy profile. So no player can do better in utility terms by changing their strategy within that profile. That's by definition a Nash equilibrium. The algorithm for finding Nash equilibrium matrix aims is quite easy. The algorithm is we just go line by line and underline the best response, payoff in the best response of the other player, and we look for the cells with double underlines. Those are our pure strategy Nash equilibrium. So it's a very easy algorithm to implement. And then in games that we solve using calculus, you already know how to find the best response function, and so you're going to get the choice variable as a function of the belief of the other player's choice variable, right? And now we're saying, well, every player's belief is going to be correct. So we can turn those bars into stars. We can turn the choice values of others into their own best responses, and then we can use algebra, substitute one into the other, and solve for equilibrium profiles. Okay, and that concludes our discussion of chapter 9.